everyone. Thank you for attending our talk. My name is Sang-kyun Kim, and we are from the VPU IP group of Intel. We are delighted to present our perspectives on designing an edge accelerator for neural networks. Deepak and I will be presenting today. I will cover the first half of the presentation, and Deepak will cover the second half. AI is a hot field these days, and we are experiencing a new era where AI is getting deeply involved into our lives. Thanks to the technology advances over the past several years, we see AI not only in the cloud, but increasingly more on the edge devices as well. And we expect the growth of AI at the edge to continue. Various sources, including those shown here, project substantial growth in the edge device market, and many of those edge devices are expected to be AI capable. Our talk will be on what to consider when designing accelerators that target this rapidly growing market. As our focus is designing accelerators for the edge environment, energy plays a key role in the design. AI inference workloads tend to be computation intensive and thus require a lot of energy. On the other hand, the edge environment is typically constrained with limited compute and memory resources and with a low power budget. Therefore, having a highly energy efficient design is inevitable for deployment of AI to the edge. Before we dive into the accelerator design, it will be useful to note how AI algorithms evolved and how that can impact the market. The figure shows how AI algorithms became more compute efficient over time, starting from AlexNet here at the bottom of the graph. AlexNet is one of the networks that had triggered a lot of interest in AI. Up here in 2019, EfficientNet can achieve the same level of accuracy as AlexNet with 44 times less compute. In a constrained edge environment, better compute efficiency enables more AI capabilities, and that has become one of the major drivers for AI applications in the edge. The plot on the right shows the AI edge inference accelerators in the market. Not only is this space already quite dense, there is a wide spectrum of power and performance requirements for various AI applications on the edge. With the ever-increasing interest in AI, here are some examples of how AI are found useful in multiple domains. In the computer vision domain, convolutional neural networks are widely used for image classification and object detection. For speech and handwriting recognition, LSTM can be used. Transformers gained a lot of popularity in natural language processing, and graph neural networks are used in social media and chemistry domains. In this talk, we will focus on designing an edge inference accelerator for convolutional neural networks, which primarily targets vision applications. However, the approach and principle we take here is general in nature for designing a domain-specific accelerator and can be applied for these other types of networks. To design an accelerator, we first need to know the computation nature of the application. For convolutional neural networks, the convolution operation dominates the compute time. So, what is a convolution? A convolution can be described as a 7-nested for loop shown on the left. A pictorial illustration is shown on the right. A convolution operation takes an input feature map of dimension h, w, and c. A filter size f and c is then applied by doing a dot product with the input and sliding across to produce an ox by oy output. This is repeated for the k filters and thus the output has k channels. As can be seen here, the core of the computation is multiply accumulate operation or MAC operation. Also, there are plenty of data parallelism, and the loop ordering is flexible, so a domain-specific accelerator should take advantage of these key characteristics. In the following slides, we will go over the design considerations for an energy-efficient accelerator, starting with the microarchitecture, followed by performance, memory hierarchy, data flow, domain-specific techniques, interconnect, and hardware-software co-design. As there are a huge number of MAC operations in a convolution with plenty of data parallelism, our first design consideration is the microarchitecture of the MAC array. One way of building a MAC array is a systolic array. The figure on the left shows a Stalock array where MACs are arranged in a mesh-like grid and data flows from left to right and top to bottom. A systolic array is a well-known architecture for matrix multiplication type of computation and is well suited for convolutions. Its simple regular structure makes it easier to design and implement, but there are some disadvantages. For example, the fixed structure makes it difficult to exploit sparsity in convolution layers. Another way of building a MAC array is by building an array of processing elements, or PE, where a P consists of one or more MACs, storage, and control logic as shown on the right. Such arrangement allows a more flexible workload distribution and is easier for sparse acceleration. However, the control and data path overhead adds complexity to the design. Another design consideration would be how to get the maximum performance within the resource budget. If resource permits, we can always instantiate more MACs. Another way to improve performance is trying to get higher clock frequency. This would require deeper pipelining and careful overlapping of phases to remove bubbles in the pipeline. Increasing clock frequency may allow higher throughput with less increase in area, but may incur more power. The number of MACs and clock frequency are just two knobs that can improve performance, and there are other parameters that can be explored for higher performance. Another key parameter in the table is the active PE or MAC utilization. The techniques discussed earlier wouldn't matter if the MAC utilization is low. To keep the MACs busy with limited memory bandwidth, it is crucial to have an efficient data distribution with sufficient data reuse. Efficient data distribution is very important for low energy as well, which we'll discuss in the next two slides. One design consideration regarding data distribution is the memory hierarchy. The plot here shows the energy costs of atomic operations used in a typical accelerator. As you can see, accesses to SRAM and DRAM are typically expensive compared to compute operations. In order to save energy, you'll want to reduce accesses to SRAM and DRAM, and for that, it is reasonable to come up with a memory hierarchy where large, expensive memory accesses are infrequent, and the small, fast memories are close by compute and accessed more often. To make most use of the memory hierarchy, we need to maximize the data reuse within each level of hierarchy. Note that the energy cost of compute is somewhat fixed, whereas the number of SRAM and DRAM accesses can vary with the degree of data reuse. So maximizing data reuse is key for reducing energy. The other design consideration for data distribution is data flow, which is how the workload is distributed among the different PEs. If you recall the 7-loop convolution we saw earlier, this is essentially segmenting and assigning different parts of the loop as workloads across PEs and across time. As the data dimensions differ from layer to layer, the optimal way of distributing data may differ as well. As a designer, you can either have a fixed data flow for simplicity or allow some flexibility to use different data flows for different layers. The graph plots the potential energy savings of having a flexible data flow for two well-known accelerators, the Google TPU and MIT Iris. The y-axis represents the amount of energy savings per layer if the optimal data flow was used instead of the fixed data flow that each accelerator supports. Obviously, it would be good to have flexibility, but the designer would also need to gauge the added cost and complexity to support that. With this, I'll hand over to Deepak, who will cover the remaining presentation.
Thanks, Sang. My name is Deepak, and I'll be presenting the rest of the slides. 3 prevalent optimization techniques to reduce memory and compute requirements for a network are quantization, pruning, and compression. Quantization is the process of mapping a large number of possible values to a smaller set of values by representing them using reduced precision. Typically, quantization is done by converting floating point operands to lower precision fixed point operands. This conversion has a significant impact on both area, as we are storing fewer bits, and on energy saving as we reduce the logic complexity of the MAC operation. The next one is pruning. It's the process of introducing zeros in activations or waits or both. Zero-valued activation or waits have no impact on the output of the convolution operation. The presence of these zeros in the neural network is called sparsity. Exploiting the sparsity can help save both memory by not saving these zeros and save energy and improve performance by skipping them during the computation. Some common network-level pruning techniques are channel pruning, where we reduce the depth of the feature map, or weight pruning where lower magnitude weight values are turned into zeros. Compression, it's another artifact of the existence of sparsity in weights and activation. Some common compression techniques are zero value compression and run length encoding, which are lossless and reduces the storage requirement. Now with higher sparsity, the impact of compression is more pronounced, and a DNN accelerator will need additional hardware to support compression. In most cases, though, the energy benefits when supporting compression outweighs the overhead incurred for the additional hardware logic required to support compression. Now let's look at the next design consideration, which is interconnect. The goal of an interconnect is to distribute activation and filter data to the PEs and drain partial sums and output activations in an efficient manner. However, building a fully connected all-to-all interconnect network to do so is highly inefficient from an area and power perspective. Therefore, all accelerators use an interconnect in the form of a hierarchy of buses or trees to construct their network of PEs and memories. All these interconnects have both pros and cons. Now, in order to address scalability, the interconnect also needs to scale to meet the higher bandwidth demands as the PE scales. This is often difficult due to the long distance wiring and the physical design challenges. Some of the capabilities that a DNN NOC must have to address these challenges are, firstly, allowing large data transfer sizes. Secondly, designing topologies that are aware of the on-chip components and rely on modular designs. Thirdly, enabling data distribution that is suitable to the mapped data flow and maximizes reuse as shown here through unicast, multicast, or broadcast. And finally, a NOC that imposes very low implementation overhead and does not require any complex interface protocols. Another consideration is hardware-software co-design for improved efficiency. Let's look at one such example, which is Brainwave, a scalable microarchitecture from Microsoft, which has a parameterized soft vector processor, which is synthesized onto the FPGA. People use Brainwave to design solutions for the DNN by first creating a custom data flow graph and then mapping them to the soft vector processor and memory in a manner that reflects the data flow of the neural network. In this picture, you see the custom data flow on the right for a neural network on the left and how it is spread on two FPGAs that are working in parallel. The data flow graph is captured by producing a stream of instructions from their compiler that is then run on this customized hardware accelerator built out of the soft vector processor and memory. This work on Brainwave shows how to build custom hardware by doing hardware-software co-design where the boundary between hardware, which is on the FPGA, and software, which is their instruction stream, is decided by the custom data flow graph for a given neural network. Let's take a look at the physical area allocation of a typical DNN accelerator. Here is the floor plan of Google's Cloud TPU. This is not an edge device, but it is indicative of the budget for accelerators. As you see, most of the area is allocated to compute logic and the memory to feed this compute logic and store the results. Given this, in order to scale the accelerator, we need to scale logic and memory. However, process scaling for logic is much faster than memory, which limits the frequency and hence the performance. Another factor that affects scalability is the NOC, as we saw earlier. A solution to this scalability problem is to put together an IP of compute plus memory that can be hardened and replicated many times through a notion of tiling to build an accelerator, and furthermore, a system of many such accelerators that can work together in parallel. Let's look at what to expect in the future. Some of the emerging techniques in the future will focus on drastically
Hello. There is one question from Shubhrita. Anyone there?
You just ask and answer.
Okay, I have a question regarding this design concentration data flow. Hello.
ये बेसिकली ये चल रहा है आपका 5 मिनट
ये डिले तो बहुत
सर
है।
डिले आएगा सर ना डिले रहेगा सर 2 मिनट रह गए नेक्स्ट सेशन स्टार्ट होने में 2 मिनट 11:27 you have to share and start
I got the point, but same thing में let's say कि सेशन 2 में कुछ क्वेश्चन आंसर है तो वो हम नहीं चेक कर पाएंगे जो आईटी को आईटी होस्ट कर रहा है या आईटी ट्राई कर रहा है अच्छा उनसे मतलब
they will do it there अगर हम तीनों हम मिला के करेंगे तो फिर वो हो
और देखो
जाएगा
इंटरफेरेंस
ये सबका एक टाइम पे तो नहीं आएगा
नहीं आगे पीछे
सर इसलिए मैंने 3 सेट्स किया तो मैंने 3 इंडिपेंडेंट किए 3 ऐसे बनाए तुम्हारे पास कोई टैब होना चाहिए क्वालिटी वाले और टिकट वाले क्या क्या
एग्जैक्टली वो उसको मॉनिटर करने के लिए हम एक सिस्टम पे लॉगिन करते हैं
तो वो तो मतलब डायरेक्टली यहां पे लॉगिन हो जाएगा अब माइक पे YouTube पे जाएगा
मेरा तो
क्वेश्चन पूछा वो तो एग्जैक्टली रियल टाइम में जाएगा ठीक है क्वेश्चन सुनाएंगे वो डिलीट नहीं वो रियल टाइम बेसिकली हमारी तरफ से पूरा ब्लॉक जा रहा है वहां पे जाने में टाइम लग रहा है पर पूरा ब्लॉक एक साथ दिखेगा
Of the result. Hello all, My name is Nisarga R, and me and my co-author Javed have worked together on a 0.6 volt second order low pass GMC filter using CMOS inverter based tunable OTA with 1.114 GHz cutoff frequency in 90 nanometer CMOS technology. These are the contents. So first I will be talking a few words about OTAs and then moving forward with literature review and the summary of the results. Then I will be talking about the methodology used in the current work and how the operational transconductance amplifier design is made and how it works, followed by the use of OTA in second order low pass filter design and the simulation of the same. Then there will be a comparison of previous works followed by conclusion and references. As we know, the scaling of semiconductor technology has allowed continuous time ICs to operate at very high frequencies while consuming low power. In the next paper, design of low voltage CMOS two-stage operational transconductance amplifier has been proposed. In this, a low voltage feed-forward compensator are one such family that have low power consumption and can operate at high speed when compared to the traditional active RC circuits. The reason that GMC structures have this ability is that they use the transconductance in open loop mode, whereas in RC structures, active elements like op amps are used to create a local feedback network. Ideal OTA is an voltage controlled current source, that is, any change in voltage will give us the change in output current. OTA is the basic core for many continuous time signals. They are used in many applications such as in oscillators, comparators, GMC filters, programmable gain amplifiers, data converters, and many more. Below is the literature review on the most recent 5 papers that are related to the current work. The first one is design and simulation of tunable low pass GMC filter with 1 GHz cutoff frequency based on CMOS inverters for high speed telecommunication applications. In this paper, the author has presented a new tuning circuit in order to compensate the effects of elements mismatch and temperature variations on OTA. A single stage high frequency low voltage OTA has been developed using 90 nanometer technology. In this circuit, CMOS inverters are used and it uses a common mode feedback structure. An additional circuit for bulk biasing is used, which is bulk voltage tuning circuit. So this helps in the transconductance tuning of the circuit. The next paper is design of three-stage operational transconductance amplifier in 90 nanometer CMOS. In this, a simple design for bulk-driven three-stage OTA was proposed in 90 nanometer technology. The first stage was a differential stage followed by 2 stages of common source stage in order to get the linearity and the rail-to-rail swing. In the next paper, design of low voltage CMOS two-stage operational transconductance amplifier has been proposed. In this, a low voltage feed-forward compensated two-stage operational transconductance amplifier is presented using 180 nanometer technology. The current replicating branch is with scale down transistors is used to implement the push-pull output stage that will give maximum output current several times higher than the bias current. In the next paper, linear input range extension for low voltage operational transconductance amplifiers in GMC filters, a folded cascode type of adaptive common mode feedback OTA is presented, and it has been designed using 130 nanometer technology. In this paper, a new type of linearization technique is proposed where two unbalanced differential pairs are used and an external adaptive bias voltage generation circuit is used. In the next paper, modeling, design and analysis of high CMRR two-stage gate-driven OTA using 0.18 micrometer CMOS technology, a gate-driven two-stage OTA with differential mode inputs is presented and has been designed using 180 nanometer technology. 1.6 volt supply is used, and in this circuit there is no external or additional voltage source for biasing. This is the brief results obtained from all the 5 papers discussed. From the results obtained from the previous papers, the problem statement was developed. So the main aim of the paper was to design and develop an OTA using CMOS inverters as voltage control current source in 90 nanometer technology and using 0.6 volts. Also, aim was to achieve voltage tuning within the circuit and to optimize bandwidth and gain in low voltage without compromising on the performance of OTA. The advantages of using CMOS inverter based OTA is that it provides good linearity. Also, CMOS inverters can be synthesized by digital tools. It is suitable for low voltage applications, and also the circuit can be very less complex as CMOS inverters have only one NMOS and one PMOS in their design. The tool used throughout the experiment was Cadence Virtuoso. Design of operational transconductance amplifier. This is the schematic of OTA developed and designed. So to design the complete circuit of OTA, effort was kept to keep all transistors in saturation. Current equation was used to keep all transistors in saturation and to get the W by L or sizing of all transistors. The OTA has two inputs Vi minus and Vi plus. These are followed by two inverters which are responsible for converting voltage into current. This is followed by a cross-coupled pair of inverters where the current is converted into negative resistance. The negative resistance helps us obtain positive gain. As the circuit was having more CMRR, a feed forward as well as a feedback structure both are implemented in the design. This is the feed forward structure and this is the feedback structure. To eliminate the external use of biasing circuit, a reference voltage Vref is provided which helps in tuning of the OTA. This is the symbol of OTA and this shows the connections done on OTA symbol for its simulation. Using the OTA, a second order low pass filter was designed to measure the results of low pass filter. The load capacitors value and the cutoff frequency was designed using the equation 3 dB cutoff frequency is equal to transconductance divided by load capacitance. Here is the DC simulation of low pass filter for 0.9 volts. When VDD of 0.9 volts is supplied with reference of almost is equal to VDD by 2, that is 0.4 volts, we obtained a DC gain of 52 dB with 3 dB cutoff frequency of 116 MHz with its unity gain bandwidth of 3.69 GHz. Similarly, when this simulation was done for reference voltage of 0.25 volts, DC gain reduced to 21.2 decibels and the cutoff frequency increased significantly to 561 MHz. Also, the unity gain bandwidth increased to 4.8 GHz. When the same simulation was done on 0.6 volts, we obtained a 3 dB cutoff frequency at 1.114 GHz. This slide shows how the variation of tuning voltage Vref affects DC gain and the bandwidth. As we can see, the Vref tuning voltage is varied from 0.2 to 0.5 for both experiments on 0.9 volts and 0.6 volts. As the tuning voltage or Vref increases, the DC gain also increases significantly, but for 0.9 volts after a high reach peak, it starts to decrease. The bandwidth operates inversely when compared to gain. As the tuning voltage or Vref increases, the bandwidth starts to decrease. This slide shows the comparison of the current work with the state of art. Here, along with the CMOS inverter based OTA, the OTAs that were designed using general method are also compared. From the comparison, we can see that we have obtained a 3 dB frequency that is pretty much higher than the previous works. Also, the DC gain value can be measurable. This table shows the comparison of CMOS inverter based GMC filters of this work with the other two works. So both with 90 nanometer technology, the filter design of order type 2 when compared to the previous of 4 and 5 designing a low pass filter, we have obtained 1.114 gigahertz frequency.
Rohit,